In this video, we are going to just run through an example of how we can use our binomial theorem in order to evaluate a binomial expansion that typically would be tedious to do the long way, so we're going to use patterns in order to evaluate this. So I say let's expand the binomial expansions to include initial coefficients other than 1 in this video. In our last video, what we were doing was we were taking things like a plus b to the nth power, a binomial to the nth power, and expanding it. What I want to do is I want to have initial coefficients that are non-1. So for instance here, instead of a plus b, we'll have like maybe 2a plus 3b. Okay, so let's go ahead and write out what we know here. First of all, the thing we want to recognize are what are our first term, our second term, and what is the power we're taking this to. So I'm going to go ahead and scribble these down. The first thing I want to admit is this. We are carrying this out to be to the third power. It's very important that we actually know what our n value is here in terms of this binomial to the nth power. Okay, and then also this, we say our first term, I suppose we could say our first term here is like 2a. Usually I would say a is 2a, but that would be redundant. But we have 2a and we have 3b. These are going to be our terms and our expansion here. So I'm going to kind of leave these off on the side. But we say, okay, so what would this expansion look like? Well, now, first things first, if we're going to be raising this to the third power, then we'd say that this expansion would look like this. We'll start with the first term getting all of the power, 3, and the second term getting none of it, 0. And then we say, okay, moving on, we say, all right, well then it'd be this thing to the second, this thing to the first, plus now the next term would have our first thing only to the first, but now our second thing to the second. And then we say our last term here would have our first thing to the 0 power and our second thing to the third. So you can see that our first pattern in our binomial expansion is that whatever our n value is here, our first term is going to start off with all of that power, and our second term is going to have none of it. And then we're just going to trade off as we go from the left to the right. We say 3, 0, 2, 1. 1, 2, 0, 3. So then we can be done when the second term contains all of the power. All right. So now I'm going to fill in what we actually know about these terms. We say, well, our first term here was 2a. So I'm going to go ahead and fill these in. We say 2a, and our second term was 3b. So we're going to go ahead and fill these in. We say 2a, 3b, 2a, 3b, 2a, 3b, 2a, 3b. Now, that's pretty easy to do. A lot of people, however, in my experience, when they do this, they tend to forget that what we now need to do last is go and fill in what these coefficients would be, okay? And so these coefficients, recall that we can use what is called Pascal's triangle to find them. Now, Pascal's triangle starts with a 1. If you're not familiar with it, it starts with a 1. It has 1s on the outside of it here, but it goes 1, 1, 1, and then it goes 1, 2, 1. So you notice I have 1s on the outside still, but to get this middle 2, what I'm really doing is I'm adding these two 1s together and I get 2. So my next row would start with a 1 on the outside. I would say 1 plus 2 is 3. 2 plus 1 is 3. Okay. And then on the outside I have a 1. And so this pattern actually continues. 1, 4, 6, 4, 1. We could carry this out for good. We could say 1, 5, 10. 10, 5, 1, just by summing terms, okay, to get intermediate terms here. So that being said, we say, well, why am I writing this out? Well, what I need, since n is 3 here, the third row of Pascal's triangle. Now, what I mean is not the third row is 1, 2, 1. Technically, we say that the first row is always considered to be corresponding to n equals 0. So we have n is 0. If you were taking something to the first, you'd have coefficients of 1 and 1. If you were taking a binomial to the second, you'd have coefficients of 1, 2, 1. We are taking a binomial to the third power. So we are going to go refer to the third row, technically, of our Pascal's triangle. And what we get here is 1, 3, 3, and 1. So we're going to go ahead and put our coefficients on this here. 1, 3, 3, and 1. So I want to mention something on this video that I didn't mention in the last video, but it's this. Wait a minute here, Pascal's triangle always has 1s on the outside. So does this mean, when we expand a binomial, that our coefficients here and here on the beginning and the end of our expansion should always be 1? And the answer to that is simply yes. You'll always have a 1 there and there. So, sometimes I get people that just neglect to write those altogether because, they say it's not necessary. But in this instance, I do want to write them to be technical. So this right here, I can tell you this, if you can learn to do this, your teacher or your goal that you're trying to achieve here, both of those will be satisfied, I'm telling you, because this expression here is exactly what we need. But what we want to do is we want to get in the habit of simplifying this. So by simplify, what I mean is this. Well, 1 times anything is 1. So we're not going to write this 1, but I have 2a to the third power and 3b to the 0. So first of all, this 3b to the 0 can be neglected. I'm going to switch over to a different color here, and I think that that's probably a little too similar to the one we had before. How about a bluish? So we say this is to the 0, and while we're at it, why don't we cross this off? That's to the 0. We get to neglect those. So now using our rules of exponents, we have a product to a power here. So 2 to the first, a to the first to the third, we would have to say that's 2 cubed, a cubed. And while we're at it, we might as well tell ourselves what 2 cubed is, which is 8. We can go ahead and write this as 8a cubed. So 2a cubed is 8a cubed. So this term, done. It's right here. We say plus. Now looking over here, we get 3 times 2a squared would be 4a squared. 4a squared. Plus now, so this term's good. We say the next term is 3 times 2a to the first times 3b squared. So I'm going to take 3 times 2a here, and I'm going to get 6a. I might as well do that. And then we say 3b squared, that would be 9b squared. And we say finally plus 1 times 3b squared. Well, 3b squared, 3 squared is, 3b cubed. 3 cubed is 27. And b cubed, of course, is b cubed. So am I done simplifying? No, this is still correct, but I think we could go a step further here and simplify more of these coefficients. So really our final expanded binomial expression here would be 8a cubed plus 12a squared plus 6 times 9 would be 54. So we get 54, a to the first, b to the second. Okay, and actually, now that I notice this here, we took 3, this was 4a squared. I forgot to put the 3b on the end of this. I'm like, wait a minute, this needs a b. So now we get 3 times 4, which is 12. 12 times 3 is 36. My apologies. So we 36, and we have a b here. We did need a squared b. And then we have 54ab squared. And then we say now plus, and we say over here 27b cubed. So just to be clear, and I feel really bad now that I did this, I forgotten to put this 3b down here. We took 3 times 2a squared, which is 3 times 4a squared. But let's go ahead and write this one more time a little bit more neatly. We say 8a cubed plus 36a to the first, a to the second, b to the first, plus 54a to the first, b squared, plus 27b cubed. So you'll notice that these coefficients are different than what are in Pascal's triangle, but the reason why is because we had initial coefficients instead of 1 and 1 in here. We had initial coefficients of 2 and 3, which are going to change the 1, 3, 3, 1 pattern that we had to begin with. But you'll notice this in terms of our variables here. We have a cubed, a squared, b to the first, a to the first, b squared, and b cubed. So that pattern still exists. So this is our binomial expansion for 2a plus 3b to the third power. Cheers.